Well, we finally reached the end. This is the fourth video discussing the reactions of enols and enolates. We're at the very bottom here with this video. We'll be looking at enolate ions, not attacking class 2 carbonyls, ketones, and aldehydes, but we'll be looking at Claisen condensation reactions where we are attacking esters and carbonates with these enolate ions. So it's a reaction that's very much like aldol condensation, which we saw to form enones in the third video, but it's actually a more favored reaction. We'll talk about that. It's favored over aldol conditions. If you can have Claisen versus aldol condensation, go Claisen. Claisen is a favored reaction over aldol condensation. So we're going to look at Claisen condensation, decarboxylation, and then we're going to end with some reactions that are really not new, but just bring together in sequential manner, back-to-back, reactions that we've learned. Acetoacetic ester synthesis, we're going to form, with that, we're going to form ketones. Ketones are formed with acetoacetic ester synthesis. Malonic ester synthesis, it's kind of funny. I mean, you'd think, well, you form a malonic ester because that says malonic ester synthesis. No, you form carboxylic acids. I know it's kind of odd to say acetoacetic ester synthesis, but they're really talking about the reagent that we start with. Acetoacetic ester synthesis, well, we're synthesizing ketones. And malonic ester synthesis, we're synthesizing carboxylic acids. Alright, so if you've made it this far, you're 130 minutes into this discussion on enolates. We've had some long videos. First one talking about big picture, form an enol or enolate by going to the alpha protons. No alpha protons, non-enolizable. Some discussions of alpha halogenation were given involving enol. And then we looked in the second and third videos with the reactions of enolates. We're on the fourth one where the enolate is still the focus. The enolate ion attacking what? Esters and carbonates. And then finishing off with some reactions involving acetoacetic ester synthesis where we make ketones. Malonic ester synthesis where we make carboxylic acids. Alright, so let's go into Claisen condensation. Again, this is favored over if you have the ability to do two or have the possibility for two different types of condensations. This is favored over aldol condensation, which we looked at in the third video to make enones. This is favored over that type of condensation. Just like aldol condensation, we still need two alpha protons to go. This was going to enones. Aldol condensation went to enones. Claisen condensation, just like aldol condensation, requires that we have two alpha protons for that reaction to be favored. So let's look at our first mixture. Esters with esters. Now, in this case, we better not use sodium hydroxide to form an enolate. The reason being, we don't want to have, I guess, a carboxylate just formed right away. If we use sodium hydroxide, I've just shown the two esters. It's the same ester, but just split them apart so we can show a little bit of the mechanistic detail. If we use sodium hydroxide, that could attack as a nucleophile, replace the OCH3, and have a OH here that can be deprotonated to make a very stable anion. The weak base carboxylates would be just favored, and you wouldn't go anywhere. This strong base would go to weak base and you're done. Sort of like Toonces the driving cat would drive this thing right over the cliff. Going to carboxylates. We'll just call carboxylates sort of Toonces. We don't want to go to Toonces town. We don't want to go to carboxylate. We want to go to beta ketoesters. Alright, so let's just show the balanced reaction. This strong base would tear a proton off, make an enolate. We would sub out in a acyl substitution reaction. We would sub out the methoxy group here, and our nucleophile minus 1 proton would be our acyl substitution product. Now it says in this note here that 2 alpha protons are needed. I'll talk about this when we get to the Deichmann reaction down below. But to sort of summarize the full reaction, yes, 2 are needed, but we're going to put 1 back onto this carbon when we go to acid workup. So you actually take off not just 1, but 2 to an intermediate product after reaction 1. But you work it up by putting 1 proton back on from the acid. We'll talk about that later. I just wanted to show just the balanced reaction. Make sure you've underlined in one of the esters the leaving group, the enolate ion. We would form, taking a proton away from this carbon, it would attack, replace this methoxy group, and in the end, this nucleophile would lose a proton to the leaving group, and we would be done. This is our what's called our Claisen condensation product, our beta keto ester. Alpha beta position, we have a ketone that's off of this ester. It's called a beta keto ester. This would be our, in this particular case, our Claisen condensation product. So we would have gone to enolate ion from this one, and we could show it here. We could say, well, I'll separate. Okay, now I apologize. These are esters are the same, but here we've taken a non-enolizable carbonyl and we've mixed it with a different ester. So we have a ester that can go to enolate and one that cannot go to enolate. So we've again used methoxide, not NaOH, because we don't want to go to Tooncestown. We don't want to just replace methoxy groups with hydroxy groups and have a proton ripped off. We don't want that. Should have done my tagging here. So we have a strong base. We can form, just going to talk a little bit more mechanistically than we did upstairs. We can form in the first step an enolate ion. There would just be an itty bitty amount of this because esters are not very enolizable. They're less enolizable than ketones because they're just less reactive in general. But we've used a strong base to give us an itty bitty amount of this, and you say, well, could it have attacked the carbon instead of a proton? Well, if it did, it'd give us nothing new. That's why we used methoxide, just in case he gets confused and goes, well, no, he's going to go wherever energy takes him. He could tear off a proton from the carbon, or he can hit this carbonyl. But if he hits the carbonyl, we get nothing new, because it's a methoxide replacing a methoxide. But if he acts as a base, we get our little bitty, itty bitty, amount of enolate ion. That enolate ion can be our nucleophile. It can sub out the leaving group by attacking. This would be our second step. Attacking, making the tetrahedral intermediate, and we'd get our acyl substitution product. Now what I want to do here, I guess again, it's just mentioned, we would not have just 1 proton ripped off. There would be another one ripped off from this carbon. We always need 2, so he had 3 to begin with. He has 2. We can get to the acyl substitution product. We have our leaving group here, and the acid would have been used to give one of these protons back. I'll show you what I mean here when we go to the Deichmann reaction, which is just an intramolecular Claisen condensation reaction. I'll show that here. So let's go ahead and say we've got now 2 esters like we have upstairs, but now they're just tethered together. So this is not going to be a new reaction down here, the Deichmann reaction. We just have the esters tethered together. This is still a strong base, and we've used OR so that we would never have something new if it attacked the carbon. So we're going to attack, just as our first step, we're going to attack the alpha protons and make a little bit, itty bitty amount of the enolate ion. Now this enolate ion can come and attack itself, an intramolecular condensation reaction. Now we may want to go ahead and number, just so when we draw the product over here, we take care of where things are hanging off of. So if you don't mind, what I'm going to do is go ahead and go through the whole reaction just up to the point of kicking off the alkoxide. So we're going to have, of course, this is our leaving group. This is our nucleophile that we're bringing in. So I'm going to have this kicked off. So we're going to have OR minus kicked off. And we're going to now draw a 6-membered ring. We're off of 1. I'm going to put 1 at the very top. Off of 1, we reestablish the carbonyl if it's acyl substitution, and it is with Claisen condensation. We have acyl substitution of this methoxide. So 1, and then come to 2, 3, 4, 5, 6. Now 6 has off of it the rest of the structure that was dragged along with the nucleophile. This part did not change, so I have to show it off of carbon 6. 5 didn't have anything off of it, 4 doesn't have anything off of it, neither does 3 nor 2. 1, we reestablished the carbonyl, but this leaving group has left. All right, so this is not the product. Now this is important. This is not the product of the first day's reaction, nor was it up here or up here. What happens is, if you notice, having two carbonyls beta to each other, meaning just in a 1-3 relationship, 1, 2, 3. This carbon right here, how many protons does he still have? How many protons does he still have? Just 1. He has 1 more. He had 2 to begin with. We said 2 are always needed for Claisen condensation. If we take that 1 proton off with our leaving group, so I'm going to go ahead and draw it as this leaving group that's a strong base. He's no weaker than the original because it's still an OR. That strong base, if he reaches down and grabs that 1 proton and leaves a negative behind, so I'm going to go ahead and have him grab that proton. That's really a better stopping point for the reaction because we'd go from strong base, the leaving group has now become neutral, has the proton. This is a weak base. Oh my land, this is wonderful because aldol condensation never had a weak base as a final resting place. You always made just your strong base back. That's why Claisen condensation is favored. If you look really hard, you can see that the anine's actually smiling, and there are eyes in the oxygens of the carbonyls. So this guy actually has a face that you can see when you go down to the X-ray crystallography. The negative charges are showing up as lines, and they have little curves on the end because this anion, when you look at it from X-ray crystallography, it looks happy. No, I'm just joking. There's no lines or positive charges down there, but I just thought I'd have fun. This is our happy, I guess, I don't know if this is right, happy face enolate ion. He's very happy because he's stable. We have a negative that can delocalize to this oxygen and to this oxygen. We have resonance that stabilizes this negative charge. Alright, so I said that was a really important part of the story. What would we do after the first day's reaction? Well, for every one of these, we make one of these because they're happy. These are angry, strong bases, happy negative charges. One of these for one of these. Well, in the end, I know the base has to go away. We would protonate this carbon in the end, taking them all out of the sort of the thermodynamic well that you've put them into, this structure. You'd take them out and protonate each of these carbons. But that's at the very end, when you're done, when you're doing the workup. This would be workup. You've really done the reaction with day 1. You would just put the proton back on in day 2. That's it. Let's look at 2 more Claisen condensation reactions. This is a carbonate with a ketone. We can take and have this as an enolizable structure. Replace the leaving group through a enolate ion formation. So I'm going to go ahead and take that proton off. We'll have a negative charge. We could attack, drive this off as a leaving group. have our, acyl group that we attack. This would be our nucleophile. And we've just done a Claisen condensation reaction. Now again, to do that, I would have not catalytic amounts, but I would have equivalent amounts of NaOH, the same exact base as is the OR group in the carbonate. I'd have equivalent amounts, and then two, like we said on the last slide, I would work it up so I could put the proton back on the happy face enolate ion that would have been formed here to give this Claisen condensation product. We can have ketones with non-enolizable esters. So this is a phenyl group, so it's still non-enolizable, just like the carbonate was. It's non-enolizable. This would go to enolate. We can have this attack. This is our leaving group. Our nucleophile has come in, and we could have torn off a second proton to put the happy face here. We could have done that by making sure we have equivalent amount of the strong base that's in the form that the alkoxy group is in this ester. We don't want to use a different alkoxide, and we would protonate in the end. That's Claisen condensation using a lot of different starting points. Carbonate ketones, non-enolizable ester with a ketone, a non-enolizable aldehyde, this is ester with a ester, non-enolizable ester with an ester, and ester with ester where they're just the same. I've written them separate here, but they are the same ester. Alright, well that's Claisen condensation. Let's do one more. I think we'll finish with this and maybe go a fifth video. I wanted to keep this one short. So we're going to end with decarboxylation, and we'll get the last topic, acetoacetic ester synthesis, malonic ester synthesis. We'll get that with one more video. 5 videos now for enols and enolates. Alright, so decarboxylation is just, I guess, exactly what it says. We're going to decarboxylate, CO2 this thing or whatever, of 3 oxocarboxylic acids. So we have at the 3 position a carbonyl off of a carboxylic acid. We need to have, what will be a carboxylic acid. So we're going to take and make a beta-keto carboxylic acid, or a 3-oxocarboxylic acid. We can run this reaction to make what we need for decarboxylation. We have to get to a beta-keto, alpha-beta keto carboxylic acid. We need to have a carbonyl basically at the 3 position of some type. A carbonyl here at the 3 position relative to a carboxylic acid. 1, 2, 3. Carboxylic acid and a ketone or some carbonyl at the 3 position. So we can do that from the beta keto ester by just adding now hydroxide, which is a strong base, that can replace as a nucleophile this leaving group, give us a carboxylate that in the presence of strong base would be going to tunces. You're going to have the carboxylate anion. And this is very, very stable, of course. If we take that proton away, for every one of these, we make one of these on this ester, you get a very weak base, and that's driven. And we can then put the proton back on that carboxylate after we sub out the CH3 for the OH. We can put the proton back on by just working up with acids. And we could have done this, go to the oxocarboxylic acid, by just having, instead of a base, equivalence or excess, and a workup with acid, we could have just used acid with a whole lot of water and have equilibrium drive what we've learned already as hydrolysis, acid catalyzed hydrolysis of an ester. We've just used saponification here and then work up with acid to get to this beta keto carboxylic acid or oxyacid. Oxoacid. So now, here's where decarboxylation comes in. We have to have a little bit of heat, but if we move or rotate this OH around so that it's sitting next to this carbonyl, So I'm going to redraw our 3-oxo-carboxylic acid. So our carbon here, I'm going to have the oxygen this oxygen is sitting here. So I've rotated it around, and it would naturally want to be there if we had internal hydrogen bonding possible, and we do. This is partially negative. This proton is certainly very partially positive off of this oxygen that's donating to this carbonyl, so we have a partially positive proton. And because of this hydrogen bonding being very strong, we favor this orientation of the molecule to itself. Now if this is heated up a bit, what we can do is pretty amazing here. We can say, well, let's just go ahead and transfer that proton. So I'm going to draw, even though it's lone pairs interacting with the proton, I'm going to go ahead and draw these as coming up to make that bond. That would start to develop a positive charge here, but we're going to start to satisfy that positive charge in a roundabout way. We can bring these electrons down as we're picking up that proton through this oxygen. Again, more likely using a lone pair, but just to keep the arrows simple here, I'm going to show it as if the pi electrons are coming up and bonding to that proton. And we can rotate these electrons. This is the hardest part. Hardest, not harbist. Hardest part is to get these sigma electrons to go to our carbon here, a sigma to pi bond conversion, sigma to pi bond conversion. If we do that, what our arrows say we've done, we break this bond, the proton goes to this oxygen, we break this bond, and this goes to a pi bond in this gap. So we would have on this right side, I'll just start there, we would have our Enol, and on this side, this comes back to a carbon oxygen pi bond. This is not going anywhere, we still have that. Well, that's carbon dioxide. That can float off as a gas and be removed. This enol, now I've shown the enol, but we know that would tautomerize and give us a keto. So this is the enol to keto conversion, which would happen in solution. And in the end, we release the CO2 as gas because this goes away. This CO, or carbon dioxide, is really from the carboxylic acid end of this 3-oxo-carboxylic acid. And we'd transfer the proton sort of from here to here, and then from here to here. So from here to here, but then that proton through enol keto tautomerization goes to the alpha position. And we get our ketone out, and we're done. That's decarboxylation of 3-oxo-carboxylic acids. Well, that's it. We'll stop there. We're going to look at one more video wherein we're going to use this reaction along with alpha alkylation reactions to talk about acetoacetic ester synthesis. And that, again, don't forget, the name's kind of a misnomer, or sort of doesn't make sense. We make ketones with acetoacetic ester synthesis. And we make carboxylic acids if we run a very similar reaction, the malonic ester synthesis. Bye-bye.